Yeah, if that's okay, right, Rossi, just to give us like an intro of what this is and the tech and what it can do.
Yeah. Um, okay. Well, basically, is it recording it?
Yeah,
Okay.
that's it. Yeah.
So this is the SenseGlove R1. It's our latest. So SenseGlove, we are a Dutch company. We operate in about 40 countries worldwide. And this is our latest haptic force feedback glove.
Okay.
Haptics is really what we focus on, and mostly gloves. We've released 4 products so far, including this one.
Okay.
And this is due for release on the 11th of December.
Right. Okay.
And essentially what this does is it is an active force feedback glove with about 40 sensors on the glove tracking 20 degrees of freedom.
Wow. Okay.
As well as active force feedback on 4 fingers, excluding the pinky, vibro-tactile in every fingertip and in the palm.
Yeah.
As well as tracking on every finger.
Right. Okay.
And what it is built for is for teleoperation and imitation learning.
Right.
So we've worked a lot in the VR market and also a little bit in the robotics with our earlier products. But we decided to build this one really for the robotics industry, specifically for like humanoid grippers, hands, for teleoperation and imitation learning of robots.
Right.
So yeah, that's about in a nutshell what this is for.
No, it's good. Like, can I have a go? Let's go.
I still just launched it.
Yeah, that's all right. I'll flip to the other side so people can see me. So I'm just going to move the camera slightly. Not balancing right at the moment. There we go. Okay.
So what we have here is that this hand here is a seed hand. It's, so we seed robotics. They're a partner of ours from Portugal.
Okay, so this hand here.
Yeah, this hand here. This is not our product. This is just what we're using for the demo today.
So seed robotics.
Seed robotics. Yeah.
Right, okay.
So seed is so they specialize also in building these humanoid hands. And what I'll show you here is so what you see on the screen is
I can see it here.
Tracking. Yeah. So I'm just going to fit this on. So the tracking of the I don't know if you can see the screen properly.
Yeah, no, we got it.
So you got here the tracking of my fingers. So you see here, we have adduction and abduction on all fingers.
Yeah.
So you can't see it on the hand here. So if you look at the screen, and now I want to look at the screen.
Yeah.
Here you see the the different tracking angles that we can see here with the adduction abduction.
Right.
As well as the grip. We have 20 degrees of freedom that are being tracked.
Right.
The only degree, so there are only 21 on the human hands.
Yeah. Wow.
The only the only thing that we don't track is essentially the slight rotation you get on your thumb, which is about 10 degrees, which 90% of humans don't even know they have that. And then what we have here is also, I'm going to show you what the force feedback does. So here we have motors throughout the glove. So we have 4 motors.
Yeah.
The only part that we don't have the motor is in the pinky.
Right.
And vibro-tactile here in the fingertips and the palm, as I said earlier.
Right.
If I hold this American football in my hand, you see here my hand is now being locked.
So that is locked, so you can't feel it.
I can't. I feel this, and I feel see, this is a slightly, soft ball.
Yeah.
And I'm able to slightly press into it.
Yeah.
See, and feel the level of force. That data is also being tracked.
So like it must feel like your fingers are getting pulled in the other direction. Yeah.
So that's the force feedback kicking in, and essentially so you see now I've got nothing.
Yeah.
So now I'm free to move.
Okay.
If I take this slightly harder object, I'll take this tin here. Here it's locked.
Right.
See, so what you see here is that I've got more pressure. The motors I've kicked in well, they're stronger. They're holding my fingers back much stronger.
Right.
And essentially now I'm locked here.
Right.
And the other part of the force feedback that you can't really see here is if I start playing around with these fingers, I don't know if you're going to see that. Yeah, you see. So if you see my finger here, if I pull the finger back on the robot, I've got an active motor that's going to pull my finger back.
Right.
So I have this on every finger. I don't know how close I have to get to the camera so you can actually see that.
It's very delicate.
That's the active force feedback. So it means that, for instance, this motion, you can feel it.
Yeah. So could you feel like an egg or something very, very soft? What, light or?
Yeah, so depending on, so if I would, no, that's actually a good question. If you grasp something like an egg, which has got a very soft shell, you would have to apply, measure the amount of force you're applying and get that feedback. So if you apply too much force, you'll crush the egg. But because you're getting this feedback, you'll be able to measure, how much force do I actually have to apply to just enough to hold.
Just enough to hold it,
So I'm just going to see with this board if I can do that. Yeah, so that if I see, I'm just holding just enough to hold this. If I release it a bit, it's probably going to fall down. Yeah, there you go.
And this information, this 61%.
So so we got here, we got the flex. So the flexation, you got the abduction here. The adduction. So here you got the force that we're applying and the percentage in terms of grip, depending on the position of my hand. So for the abduction force, if I hold here,
here we go.
See here, I'm on 100%. So he's holding the object. There's no need to push any further. This is how much grip I need to actually hold my objects in place. This also depends on the sensitivity of the hand. So here we're working with a seed hand. Different robotic hands will be measuring different types of data.
So depending on the actual hand, you can have different sort of levels.
Also levels of precision. Also on this particular hand, you don't have any. So you see here, if I do this movement, the abduction.
You haven't got that.
Hands,
Okay.
You don't have this tracking here. You do have it on the thumb.
Right.
So I'll have it here on the thumb.
Oh, okay. Yeah.
But I don't have it on my index, for instance, which you do see on the screen. So you see this hand is not moving.
But if you had a different hand that had that movement.
Yeah, for instance, we use like, for instance, shadow hands. Shadow hands have more abduction capabilities, and then you can really see that type of tracking also on a robotic hand. Right.
Okay. And then so I saw recently there's a whole thing about having some humanoids in the household. But the idea is that the humanoid can only do very basic tasks. So someone has to remote in with telepresence. So assuming that you use.
Well, this is kind of a solution to that. It's not kind of, it is.
It is.
We've seen, you've probably seen all those videos, them being trained with a VR headset and controllers. With very low level of precision. This solves this issue essentially. The R1, the SenseGlove R1, it solves the imitation learning issue and pain points of not having enough precision in learning for robots learning how to do precise movements. Here, it's an intuitive way for the robot to learn because it's based on the human hand. It's not based on a controller.
So it's someone trying to move.
So if you've got a human, humanoid gripper, or humanoid hand, robotic hand, essentially, if you've got the same amount of tendons, if you've got 21 or 20 degrees of freedom in a hand, we're tracking the same amount of degrees of freedom.
Right. Yeah. No, this is it. That's definitely like the user case that I can see. You put on your headset, you walk around, and then you can use it.
And then also, the fact that we have, it's not just about the tracking of the data, it's the force. The force feedback. I haven't seen any other gloves yet available, and we're releasing next week, and I don't think anyone else is.
Okay,
at
good.
This early stage.
Like you said, I mean, if you can get into that sort of industry, and that's obviously going to be a massive industry that's going to be growing. So.
Yes, no, it is, and we're getting a lot of traction right now from all these robots that need a precise way of learning how to do natural human movements.
And then sort of cost-wise for the software in hand, is it available?
The hardware prices were actually up until our launch on the 11th of December were 12,500 euros.
Okay.
That's on a pre-launch price. After that, it'll be 15,000 euros for a pair.
Okay.
So 2 gloves with 2-year license of software, free updates.
Right.
The interface is on ROS 2.
Right.
And we also have industry, and so that's for an academic. That was academic price.
Okay.
So when the university is going to publish using our product, 15,000 is the base price. And then we have industry implementation packages where we also have like a hackathon, on-site hackathon to implement into the system.
Right.
And that starts at 35K. For 35,000 euros, it can go up to, then we have custom-made packages starting at 60, and it can go up to 1 million, 2 million, depends on the system.
And then how? So we've also got Marikai on this stand. Could your system work with a platform like Marikai, or has it got to be certain sort of hands?
That's a very good question. I'm not 100% sure.
No,
If there is a hand, technically, if it's the same interface, if it's working on ROS2, I'm not familiar with the robots. This is our partner's robots. I've just been seeing it float around for the last day. But if it has a hand and the interface is ROS2, there's no reason why it can't be integrated.
It'd be something, but it'd be worth like looking at, because I think like Marikai are trying to launch across like Europe as well. So to have the ability to do what it's doing, but then do a remote presence as well would be great. So
no, absolutely. I see it's only got 4 fingers though.
Right.
Which shouldn't be an issue, because we can, you can just combine.
You can just combine a finger,
And actually, the force feedback is, the pinky doesn't have force feedback. So in terms of tracking, well, then just have to track 1 finger less. And then in terms of force feedback, it'd be the same result.
Yeah, and as long as you got the grip in it, even if that 1 finger's locked, then it should be fine.
Yeah, of course. I mean, the most important is the pinch between the index and the thumb.
Right.
So that's also why we didn't include the pinky. We had it, we could have built it in, but then it's just, it's more weight.
Right.
It breaks away it's not immersion here, but the whole point is to also have a human-centric technology.
Right.
This is 575 grams roughly per hand, when you're not wearing a tracker, because you can also be sometimes combining with a tracker.
Right.
But here without a tracker, it's 575 grams, which is a reasonable weight for a human to carry for an extensive period of time without being drained by wearing a huge piece of hardware.
And what's the tracker do?
Tracker's more for like 6 off tracking. So this is actually a Vive tracker.
Right.
So this is more like, if you're tracking in space. Because right now, as you see, it's static, right? I'm not tracking.
Oh, I see. The hand was physically moving it.
But we can combine this with, like, for instance, we work a lot with Haption. Haption they've got a haptic arm right over there, actually.
Right.
And with Haption, you can actually also have grounded force feedback. So you feel weight, we also work with them in VR. So to add like the sense of weight or resistance in an immersive environment or in a robotics environment.
So how does that work for weight, for gravity? Like if that was 1 kilogram and something looked exactly the same as 10 kilograms.
So I don't want to say anything that's inaccurate about the Haption, but how grounded force feedback essentially works is that right now, if I would, grasp this, with my hand, so I'm just going to grab it. There you go.
That's good.
Obviously, I don't feel the weight, and also the movement is independent here.
Right.
Grounded force feedback, this movement would be not only tracked, but the amount of resistance that is caused by the object, or for instance, if I'm pressing against the wall, would be also measured.
Wow.
So that means that you would have either in a virtual environment or I think in a robotics environment also. I'm more from the VR industry.
Of course,
but let's say if you're putting pressure, that's the resistance you get from resistance you get from a wall or from a hard object, heavy object, would be replicated in the haptic arm up to the capabilities of that haptic arm. Different haptic arms have different amounts of weight that can actually replicate or imitate. So depending on what hardware you're using, you'd be able to replicate a certain amount of that weight or the full load. We've done some use cases more on the VR side, where it's like a part of a surgery, where you feel the resistance of, like, when you're performing this section of a surgery, you feel the resistance of the body.
Right.
So, like, if you press on, the body, whether you're performing the operation or the virtual operation, you feel resistance because there's a soft body, like
pushing against it
on the actual body. So
that's
how in the principle of it works, is that it activates those, the parts of your body, the muscles that are normally subject to resistance or weight. So that's what it adds. So it adds another level of muscle memory, because obviously if you're holding an object and then just going to throw the dice, four, not bad. Essentially, if you're holding an object and or if you're pushing against a hard surface or wall, that is adding another layer of learning for the user or for the robot, for that matter.
So like basically another way for the user to be able to feel exactly what's going on in it.
It gives you more accuracy in the real world, precision in the environment you're operating in.
Okay, no, I think that's great. I think we got a great overview there. So thank you. I'll take you with that.
Actually, you can do this one.
Here we go. Flip it around. There you go. Perfect. Thank you.
You're welcome.